Hello everyone, this is Mr. Couple. In this video, I'm going to be showing you how to do error propagation using the techniques of IB physics. This is one of the craziest and most complicated things that we do in this class, so I thought a video would be a really good idea so you can look back to it in the future when you're doing your IA or anytime you're doing an experiment. We can look back to this video and remember how to propagate uncertainties through equations. Let's get started. A measurement of a length may be quoted as L equals 28.3 plus or minus 0.4 centimeters. So every measurement has, three parts to it. So let's look at this. So the first part right here, that's called the best estimate. And we symbolize that with the subscript naught. The next part of the measurement is called the absolute error or the uncertainty, which we call delta L. And the final part of the measurement is the unit of measure. There's one more thing that you need to know. So there's actually two different types of uncertainties. The absolute uncertainty is where you actually give a numerical value in terms of a unit with a plus or minus in front of it. So that's why it's called the absolute uncertainty, because you're saying specifically how uncertain it is. The other type of uncertainty is called fractional uncertainty, where there is no unit of measure. The fractional uncertainty is a ratio of the absolute error to the best estimate. And then there's one other type of uncertainty that you'll sometimes hear, and that's called the percentage uncertainty, but that's simply the fractional uncertainty multiplied by 100%. So first, we're going to look at this measurement. So this is a measurement of velocity, 360 plus or minus 20. So what we want to do here is write the absolute error, which is delta V. And so the delta V, or the absolute error in this velocity measurement, is plus or minus 20 meters per second. The next thing we'll do, we'll write out what the best estimate was. And that's 360 meters per second. Now we're going to calculate the fractional uncertainty. The fractional uncertainty is just the absolute error divided by the best estimate. The absolute error was 20 divided by the best estimate, which is 360. And this will give us the fractional uncertainty. Let's grab a calculator and let's throw these numbers in. Now that I look at it, we probably didn't need a calculator, but just to be sure, 20 divided by 360. So that gives us 0.055555. 0.0556. That's the fractional uncertainty. You might be wondering, well, wait, what happened to the unit of measure? Well, if you notice, it was 20 meters per second and 360 meters per second. And so the unit of measure actually canceled out. There is no unit of measure in a fractional uncertainty. The last thing we want to do is write down what the percent error is. And so to find the percent error, we just take that and we multiply it by 100. And so the percent error would be 5.56%. Let's do the next one. This is a measurement of temperature. Temperature is 310 plus or minus 1 Kelvin. That's human body temperature, by the way. Well, our absolute error in the temperature was just plus or minus 1 Kelvin. The best estimate of the temperature was 310 Kelvin. Now we're going to calculate the fractional uncertainty, which is delta T divided by T naught. For the fractional uncertainty, we calculate 1 divided by 310. We're definitely going to want to grab a calculator for this one. So I can do 1 divided by 310. We could also just type 310 and raise it to the negative 1 power. Either one of those is appropriate and they're in agreement. And so we get that the fractional uncertainty is 0.003225. So we'll write that as 0.00323. And we can find the percent error. And so if we move the decimal place 2 spaces over, multiply by 100, we get 0.323%. This is a very precise measurement. There's very little uncertainty because it's only 1 Kelvin compared with 310 as the measurement. So this is a very, very precise or low amount of uncertainty. Well, what if there are no numbers at all? Can we still do it? Yeah, of course we can. We're just going to have to write it out without plugging in any numbers. So we know that the fractional uncertainty is just, so I'll write this down. So the fractional uncertainty is equal to delta A over A naught. And then the percent uncertainty is just that times 100%. Next, we're going to actually look at how do you propagate errors. But before we do that, I want to read this paragraph to you because it'll explain it a lot better than what I just said. Often in physics, we'll use a measurement of certain quantities. Often in physics, we use measurements of certain quantities to calculate the measurement of another quantity. For example, measurements of mass and acceleration to calculate net force. In these cases, the uncertainties in the original measurements will cause an uncertainty in the calculated quantity as well. How do we calculate this uncertainty? The act of determining the uncertainty in a calculated quantity is called propagating uncertainties, and it is an important part of all laboratory work in IB physics. For calculations that involve addition and subtraction, then the uncertainty in the calculated quantity is simply the sum of the absolute uncertainties of each quantity. So let's make sure we highlight what's important here. So this is for calculations that involve addition and subtraction. The uncertainty in the calculated quantity is the sum of the absolute uncertainties of each quantity. Let's look at question 2. The quantities A, B, and C are measured and used to calculate the quantity capital Q. Determine the absolute uncertainty in capital Q for each of the following. First question is Q equals A plus B. Well, it told us in the definitions up here that if you want to find the uncertainty in Q, that's delta Q, then all you have to do is take the uncertainty, the absolute uncertainty in A plus the absolute uncertainty in B. If it's minus, then the uncertainty in Q will be the absolute error in A plus the absolute error in B. Yes, it's plus. It doesn't matter whether you plus, if you subtract or add, the uncertainty in the calculated quantity is always the addition of the two absolute errors of each quantity involved in the calculation. So if we did all three of these quantities, A plus B plus C, then the absolute error in Q would be the absolute error in A plus the absolute error in B plus the absolute error in C. Let's do an example problem. The side A of a square is measured to be 12.4 plus or minus 0.1 centimeters. Find the perimeter P of the square, including the uncertainty. Let's draw a picture to make sure we understand what's happening here. We have a square, and each side on this square has length A. And we know that A is equal to 12.4 plus or minus 0.1 centimeters. Well, the perimeter of the square is calculated by adding up the sides, which in this case are 4 A's. A plus A plus A plus A. This means the perimeter of the square is simply 4 times 12.4. And that's going to give us, let's grab our calculator, 4 times 12.4. So that's 49.6 inches. But what's the uncertainty in this calculated quantity? Well, to find the uncertainty, 4 times the absolute error in A. The absolute error in A was 0.1 centimeters. And so we end up getting 0.4 centimeters for the fractional pickup for the absolute error in the perimeter. So now let's state the perimeter of the square. The perimeter is equal to 49.6 plus or minus 0.4 centimeters. So what about multiplication and division? Well, when you're calculating quantities that involve multiplication and division, the fractional uncertainty of your calculated quantity or your result is the sum of the fractional uncertainty of the quantities involved. So what does this look like? Well, if we have a quantity Q equals AB, then this is what we know. We know that the fractional uncertainty of the quantity Q will be equal to the fractional uncertainty of quantity A plus the fractional uncertainty of quantity B. And this will eventually allow you to find the absolute error in Q if you want to. But this is the relationship that you use when you're multiplying and dividing. What if you divide? It's the same thing. The fractional uncertainty in Q is equal to the fractional uncertainty in A plus the fractional uncertainty in B. And if you have a multiplication and a division, well, it's the same thing as before. The fractional uncertainty in Q, fractional uncertainty in A, plus fractional uncertainty in B, plus fractional uncertainty in C. It's really not going to make sense until we actually solve a problem. So here's an example. The sides of a rectangle are measured to be A, 2.5 plus or minus 0.1 centimeters, and B, 5 plus or minus 0.1 centimeters. Find the area, A, of the rectangle, including the uncertainty. So let's draw a picture of a rectangle. So this is side A, and this is side B. A is 2.5 plus or minus 0.1, and B is 5 plus or minus 0.1. Area is A times B. We can find the area by just multiplying these numbers. 2.5 times 5. 2.5 times 5 is 12.5. And this is centimeters times centimeters, so the unit is centimeters squared. But what's the uncertainty in A? Well, we can't find the uncertainty in A right away. We're going to have to do a complicated process called propagating, where we propagate the error of A and B through to figure out the uncertainty in capital A in the area. We know that the fractional uncertainty in A must be equal to the fractional uncertainty in little a plus the fractional uncertainty in little b. And now we're just going to plug in all of our numbers that we know and solve for the absolute uncertainty, which is delta A, the absolute error. Let's plug in the numbers. So the fractional uncertainty in A is what we're looking for. We know what the best estimate is. It's 12.5. The absolute error in A is 0.1. The best estimate of A is 2.5. The absolute error in B is 0.1. The best estimate of B is 5. Let's go use the calculator to figure this out. 0.1 divided by 2.5, that's 0.4, plus 0.1 divided by 5, that's 0.6. This gives us the result that the absolute error in A divided by 12.5 equals 0.06. To solve for the absolute error in A, the delta A, we just have to multiply both sides by 12.5. We end up with delta A is equal to, let's grab our calculator, so 0.06 times 12.5. And we get 0.75 centimeters. So now we can say that the area of this rectangle, is equal to 12.5 plus or minus. Now let's wait a second. Remember that the absolute error in IB physics always has to be rounded to one significant figure. So I need to round this off to 0.8 centimeters. And now I can write that as 0.8 centimeters. So that's the area of the circle. It's 12.5 plus or minus 0.8. And just check to make sure that the precision in your error, your uncertainty, is the same as the precision in your best estimate. And they match, so we're good to go. The last situation we look at are powers and roots. For calculations that involve quantities that are raised to powers or roots, the fractional uncertainty of the result is the fractional uncertainty of the quantity multiplied by the absolute value of the power. So this rule sounds extremely complicated. So let's try to break this down a little bit more. So calculations that involve quantities that are raised to powers or roots, like square root of 2 or to the second power. And that happens a lot in physics, especially when you have, like, for example, kinetic energy, 1/2 mv squared. So we see these powers all the time in physics. And so we should probably know how to handle the uncertainty in those quantities. The way you do it is you say the fractional uncertainty of the result. So once again, it's telling us the fractional uncertainty of the result is the fractional uncertainty of the quantity multiplied by the absolute value of the power. Fractional uncertainty of the quantity multiplied by the absolute value of the power. Let's see what this looks like in practice. So if we have Q equals A to the nth power, what we can say is that the fractional error in Q is going to be equal to the fractional uncertainty in A multiplied by the absolute value of the power. And so the rule looks like that. Here's another one. Q equals the nth root of A. Well, it's important to realize that the nth root of something is really just A raised to the power of 1 over n. You know, this is like square root. The square root of A is A to the 1/2 power. If you guys didn't know that, there it is. So what is the fractional uncertainty in this case? Well, the fractional uncertainty of Q is equal to the absolute value of the power, which is 1 over n, times the fractional uncertainty in A. Just like that. Let's do an example. A mass is measured to be m equals 4.4 plus or minus 0.2 kilograms, and its speed v is measured to be 18 plus or minus 2 meters per second. Find the kinetic energy of the mass. Well, the equation for kinetic energy is 1/2 mv squared. So let's go ahead and just calculate the kinetic energy. It gave us the numbers. Let's calculate the quantity first, and then we'll worry about figuring out the absolute error later. So the kinetic energy is going to be 1/2 4.4 times 18 squared. That gives us the result of, let's grab our calculator, 0.5 times 4.4 times 18 squared. 712.8. And the unit is the joule. So now let's propagate the error through this formula to find the uncertainty in the energy. We know that this is 1/2 mv squared, so this is a quantity times a quantity to a power. The absolute error of E divided by the best estimate of E, that's the fractional uncertainty in E, is going to be equal to the fractional uncertainty in the mass plus the fractional uncertainty in V squared. But the fractional uncertainty in V squared is the absolute value of the power times the fractional uncertainty in V. And so you can do this still. We can add the fractional uncertainty in M plus the fractional uncertainty in V squared. But the fractional uncertainty in V squared follows the rule that we just outlined above, which is it's the absolute value of the power times the fractional uncertainty in the quantity. Now we just have to plug the numbers into this. So here we go. So delta E is going to be equal to this fractional error. So we have 0.2 divided by 4.4 plus 2 times the absolute error of V divided by the best estimate of V, which is 18. And then that whole thing is going to be multiplied by E naught, right? We're just going to multiply the E naught to the other side. And so the E naught we calculated over here, which is 712.8. We're just going to have to throw this big, crazy, complicated thing into the calculator. 0.2 divided by 4.4 plus 2 times 2 divided by 18. So that's what's in those brackets there. So now let's multiply that by 712.8. If we do that, we get 190.8. So the absolute error in the calculated quantity of the energy is 190.8 joules. But remember, we can only have one significant figure in that, so that's going to be about 200. Now we just need to make sure that the precision of our uncertainty agrees with the precision of our measurement. Since the uncertainty is to the hundreds place, then the precision of our best estimate also has to be to the hundreds place. So that means we have to round off 712.8. We have to round it off to 700. So we get that the kinetic energy is 700 plus or minus 200 joules. That's it for this video. I hope you guys found this helpful. And if you have any questions, please ask me on chat.google.com, or you can send me an email, or you can hit me up on Discord. All right, have a great day. See you later. Bye.